Okay, so as we saw in the first set of notes that I made, we looked at concrete models for fractions. And remember, one of the things we want to keep doing is thinking about using concrete manipulatives or models, which are things basically that you can actually hold, and then translating that into pictures or diagrams, or a pictorial model, and then eventually for the abstract. If you read in the book, you'll see that they talk a lot about making sure that you don't do that too fast with fractions, especially. So, of course, we have the area model, which is continuous units that are usually circles, squares, rectangles, pattern blocks. I'll show you some of that next time. Linear model, which is what we use the fraction strips. Number lines, which are also continuous. And then remember discrete models, which are set, called the set model, which this could be any kind of counter or just anything that can be counted. So a set of things that are countable. Sometimes people use egg cartons, so you can actually drop little pieces in the portions on the egg carton and use that for fractions. Okay, so a couple things we want to talk about with comparing fractions is, and we did this a little bit on the last notes when I showed you the online manipulative that you could compare fractions. So one way is to compare a fraction that has the same denominator, and that's what we usually do when we talk about getting a common denominator. So the parts are the same size, meaning the strip or whatever is divided into the same number of parts. So these are easy to compare because if you have ninths, like you do in here, then the numerator that's smaller is always the smaller fraction because there's only 5 ninths as compared here to 8 ninths. The other way is sometimes it's easier or it's quicker to compare a fraction if the numerators are the same, which we usually don't think about. But one way to do this is we're basically saying here, this is like saying we have 3 divided into 5 parts, and here we have 3 divided into 7 parts. So 3/5 here is larger because I'm only dividing it into 5 parts. So one of the ways I tried to get you to think about this in class briefly is use a context. So like if you had 3 cookies and you had to divide it among 5 people, then each person is going to get 3/5. But if you had 3 cookies and you had to divide it among 7 people, then think about that. Each person is going to get less because you have to divide the same 3 cookies into 7 parts. So again, if you use a context, you can get kids to think about that. The other way is to use what's called a benchmark fraction. Just like when we use tens, hundreds, thousands, counting by 5s and 2s, things like that, that are benchmark numbers. You can also think about fractions and later with decimals and percents. So, we use things like a half, 1, a fourth, things that are fractions that we kind of know more about. So if we're comparing here 4/5 to 2/7, we can say, well, let me use a half just to try to compare. So this one, we have a bar to show this. So if this is my unit from here to here, then 1/2 is this portion here. So I could compare 1, 2, 3, 4, 5, 4/5 to 1/2. So 4/5 is going to be this large portion, which is greater than a half. Or you can think about this, 4 out of 5, that's much larger than a half because a half of 5 is 2.5 and 4 is larger. So we know 4/5 is greater than half, and we know 2/7 is less than a half because half of 7 is 3.5. So this is less than 7, which makes 2/7. less than a half. So that means 4/5 has to be greater than 2/7. So sometimes that's a way you can do that. The other thing is to think about, again, using visuals to show equivalent fractions, and the same thing with comparing fractions to see if one's larger or smaller. So this is just another way to build this idea here with a visual, and then eventually you can connect that to this idea that we know of equivalent fractions, which is basically, if I start with 1/3, for example, if I multiply the denominator by 2, 3 times 2 is 6, then I can also change the numerator by the same amount. 1 times 2 is 2. So 2/6 is equivalent to 1/3. And you show that here by dividing this whole square into 6, and 2 of those 6 is equivalent to this 1/3. So if I could move this, I could lay it on top of here. And then if we divide it further into 12, so like for example, 3 times 4 is 12, 1 times 4 is 4. Or you could talk about simplifying 4/12 down to 1/3. That's just the basic idea. This is what I was just talking about. You can use basically a strategy, which is to find the greatest common factor. So if I want to simplify or put this fraction in the lowest terms, 84 divided by 144, or 84 over 144, I could find the greatest common factor of those two, which is 12. So this is, remember how you can factorize, find the greatest common factor. And then I just divide this by 12 to get 7, divide this by 12, oops, sorry about that, to get, you go back, divide this by 12 to get 12. So 7/12 is the lowest term for this fraction. The other way is just to write factors of 84 and write factors of 144 that multiply to give you that, and then just divide out the common factors. So that's another way, which is what I have here. If you divide by common factors by rewriting into a factorization, not necessarily a prime factorization, but just any factorization. So we're trying to get it down to simplest form. Sometimes people call it reducing the fraction, but remember, we're not really reducing it. We're just changing it into a simpler form with smaller numbers, which are factors of both of these. So here you can rewrite 28 as 7 times 4, and you can rewrite 48 as 12 times 4. And if I can show you this, then what you're going to do, hopefully this works, yeah, we can kind of divide these out. A lot of times people write that. So 4 divided by 4 is 1. So technically, you have a 1 here and a 1 here. We usually don't write that, but you want to make sure with young kids, you start to emphasize they're not canceling, meaning they go away. It's really meaning 4 divided by 4 is giving me a 1. 4 divides into 4 one time. 4 divides into 4 one time. So that's how I get 7/12, which is the answer that we got before. Okay. So, whoops. So 7/12. Okay, the other way you can do equivalence, and this is sometimes really handy if you want to do a quick check, especially when you have maybe larger numbers like this. You might have remembered something like cross multiplication. You sometimes use that when you're doing proportions. So you can show that if you can multiply this times this number, it's the same thing as this times this number. So a lot of times you'll see students will write something like this. And then that shows that you can get these multiples, or the product, I'm sorry, of those two numbers. If they're equal, then you know that the fractions are equal. So 24 times 1080 is 25,920. 36 times 720 is 25,920. So that means that this original fraction is equivalent to this fraction. We can maybe look more about that later to see why that works. But that's a typical thing that people use. Okay, so I'm going to stop here and go to an example of using Cyberchase, which is a PBS show, and they have some games online. So I found one with equivalents to show you how you can see different models and use that as an example for kids. Okay. All right, so hopefully I'll have time to do both of these. This is called Melvin's Make a Match, and it's on Cyberchase, you can see, and I think I have the link on Web Links on Blackboard. I'm not going to play the whole game, but you can see basically you hit play game, and it'll take you through different levels. And it might be small when you guys are seeing it, but you can go there yourself. You go to Cyberchase or pbskids.org, Cyberchase, and you go to find it, and you can look under fractions and find this Melvin Makes a Match. But what you can see is they have fractions written, but then they also have models that sometimes are area models and sometimes they're other models. And what you do is hopefully you can still see that. You find it, you put it on the balance and try to match it. So for example, I can put 2/4, oops, I'm not being able to get it. Okay, there we go. So this is 1, 2, 3, 4, 5, 6, 7, 8, 4 eighths. So then I check and he says you're right. And then you can keep going, although I can't see, oh, I have to keep going here. So this is 2/4, it looks like. And then bingo, you keep going. 7 eighths, that's obviously pretty close to 1. And then the last one is 3 eighths. And then it'll take you to the next round, which has more. So you're seeing this area model, and you have to see that all the parts have to be the same, meaning each portion there has to be the same, and then I have one shaded. So this is 1/4, so I want to click on 1/4. If you don't get it right, so let's say you do 2 eighths, and then you click on this, they bounce them back up. So that's kind of cool. And then it basically just gets a little more difficult as you go along. You get more pictures. So this one is what? 3/6, it looks like. And you keep going. Okay, so you could go and play that if you like, Melvin's Make a Match, and it's on the Cyberchase site. I want to show you another one, so I'm going to pause for a second. Okay, this is on the mathplayground.com site, and I think I also have that because I had you do the prime factorizations last time. So this is the equivalent fractions game, I guess. And it's kind of cool because what it asks you to do is find a fraction between 1/5 and 2/4. So to do that, it's easy to compare 1/5 and 2/4 if we get the same denominator. And in this case, you have to find the least common denominator. So what you do is it tells you here, rewrite the fractions using the least common denominator. So I put in 20 here, and 4 times 5 is 20, so this is going to be 2 times 5, which is 10. And then you move this to represent that. So you move that to 20. And I might only be able to show you one because I think I'm running out of time. Here, 5 times 4 is 20, so 1 times 4 is 4. And you move that again to 20, and it'll change the bars, and you can hit check answer and see if you're done, if you're correct. And the reason I like it is because it gives you a number line, and then you can see there's lots of fractions in between between 2/4 and 1/5, because 2/4 is 10/20, which is a half, and 1/5 is 4/20. So there's 5/20, 6/20, 7/20, 8/20, 9/20 between this fraction and this fraction. So this is really cool because a lot of times younger kids don't realize there's lots of fractions. In fact, there's an infinite number of fractions between these two. And I'll talk about that again later and refer back to this so I can get you to see that in another way. So then you can go to a new fraction, and I think that's it because I'm getting ready to run out of time. I want to post this, so we will continue with this next time.